I'm closing the editor and I'm generating the editor again. And I am restarting the editor. After starting the editor, the model file is still there, and since we only expanded the grammar, it is still valid and we can add our port definition. So and as you can see, we have a full code completion. The editor knows which keywords could follow and it gives us a selection. Now we want an import, it has a name, and with the full code completion we get a selection of the defined interfaces here. The resulting model is again represented in the outline view. In the next step we would go on by defining the code generator for ports. In our showcase system, we also model the ECU, bus topologies, and mapping of logical messages to bus messages. Typing all that would take quite some time, so I have prepared a full grammar and code generator to show you the next steps. Now we have a more complex model with more interfaces, more components. The model contains the possibility to model instances of components and their connection through the ports. It has constructs for modeling a bus topology with ECUs and different types of buses, the deployment of logical software components to ECUs, and constructs for mapping the logical signals to bus signals. So I'm going to start the code generation for that kind of model. And we see the pieces of code that are generated. For example, we get a .h file for the definition of variables that can be used for data interchange within one ECU. And we can see that we generate code for define statements and function prototypes. Obviously, these are only examples. You can generate any code in any language, be it C, be it Java, with a template-based mechanism. And to show you one of the benefits of the model-driven approach, we will have a look at the model change. We see that we have generated one global variable called speed from within the model, and this is generated through that interface. And now imagine that we have a model change. We need to bring in more signals. We do not only want to transmit speed, but for example RPM or the actual gear. So now in the manual coding approach, we would have to go through all those files and bring in the new signals that we send. And with a model-driven approach, we just enhance the model. I have prepared the other model. It just contains new signals within the interface volatile. And by generating the model again, we see that the code is going to change. If we go to global signals, we see, oh, there's a number of new variable definitions, and of course all the other files have changed as well to accommodate the new model. So the manual coding of that would really be tedious and error prone, and you can increase the speed and the quality by the model-driven approach. Obviously, this isn't only limited to introducing new signals. You can add new software components, and you can, for example, generate a total different infrastructure. This approach does not only work for embedded systems, but for application systems as well, where by the generation of a middleware layer you can easily replace one database with another, for example. With that generation in an embedded systems, you can easily introduce code generation for new embedded operating systems or for different platforms. More information about the model-driven approach in various domains can be found on our website. So this was the second screencast in our ITEMI screencast series on model-driven software development. The next screencast, number 3, will show you how we work with the generated files that come out from our model and continue in the Eclipse development environment for C, CDT, to actually compile and flash all that software down to the actual hardware and get a running system out of that.